So we're talking about mole concept here. We're talking about the development of the theory of tiny little particles. And it was so very, very important for chemistry to happen. See, chemistry was not, okay, a discipline that people respected or one that actually worked until 1860-ish, when we developed an idea that atoms do exist because of a basic mole concept, a way of counting these particles and using them to predict. See, chemistry wasn't a science we could actually predict and do any math. And again, a science is one where you have some laws that you abide by, and from those laws you can predict and do some pencil and paper type of predictions and calculations. And so chemistry for a long time was just a science of just trial and error, or alchemy, hey, that works, that doesn't work. Until we can actually predict what happens in reactions, it really wasn't a science yet. So in order for us to do the mathematics and analytical chemistry, the mathematics done today, we needed two things. We needed first a belief that there are these particles that are coming together and separating in reactions, and a way to count them without actually counting them because they're so gosh darn small. So we need to go through history to show really why it developed as it did, and all of the underlying themes and pressures that prevented atom theory, atomic theory, and of course mole theory to lack of persisting. Okay, so let's start with Democritus. We're starting with the Greeks, and we're talking about the philosophical differences here between two contemporaries. Democritus was, they said, a materialistic person, in the sense, a materialistic thinker, I should say, more importantly, in that basically believed that everything is a result of natural laws. So his thinking was more about the idea that, or this philosophy was centered around the fact that we are here because the laws of physics, or the laws of the universe, okay, are allowing life to exist. Whereas his contemporary at the time, Socrates, okay, who you probably know, okay, was essentially put to death, his contemporary at the same time period was a believer, a philosophical thinker based upon the human, ethical, moral standard from the perception of human thoughts. And of course, Plato was a student of Socrates, and Aristotle was a student of Socrates. And Plato actually said that he wished he could burn everything of Democritus, meaning that their thinking, which was centered around the human being and their perception and thought, was so far different around Democritus' idea of laws of physics. And of course, before we go back or go away from Democritus, he was the one, or his teacher, they say, coined the word atomos, and that all things are made of these indivisible particles of matter called atoms. And of course, that's where you hear this from. And he's a jovial character. That's why they're supposed to the bust he's laughing. But that's how he explained many things. In fact, he went as far as supposedly in his writing to talk about the tongue tastes things based upon these atoms and their, I guess, way of interacting with the tongue. So he certainly was ahead of his time, even though there was no experimental evidence for that. So, but this is so very important to understand why it took so long for chemistry to come to the forefront. Again, we could not do any mathematics or any kind of predictions with any certainty of laws with chemistry. It was just a, hey, does this react and how much? It was trial and error because we didn't have the concept of particles accepted, and we didn't have the idea of how to count them. So this mole concept that I'm teaching you today, okay, is ingrained with history. So let's continue. So Socrates, Plato, and Aristotle, the big three thinkers, they're connected because Plato was a student of Socrates, Aristotle was a student of Plato. They led this movement of thinking centered around the being, the human, okay? And certainly they themselves were very, very bright and ingenious people. Now Alexander the Great, okay, the leader, the young leader that basically expanded the Greco-Roman Empire to almost the entire planet at the time, civilizations, okay, Alexander the Great was a student of Aristotle. So he, of course, took on his teachings and spread them throughout the Western civilization. So Western civilization was founded with the ideas that stemmed from Socrates. And part of the idea is the thinking that, hey, okay, if we can't visualize it, we can't perceive it with our mind, it probably doesn't exist, as opposed to Democritus, who said, hey, we're here in living form because the laws of physics or laws of the universe are allowing it, or on our special case. So a different way of thinking. And of course, the thinking from these big three through Alexander the Great to the Western civilization was that atoms can't exist. You can't see them, so why would you think that they existed? Okay? So for a long time, and this ideas here, stemming from Socrates all through the early Western civilization, held the belief that science was central to the person. Okay? And we know about this because there's been some scientists who were actually jailed because they're the ideas that weren't centrist to that idea. Okay, so unlike Aristotle, Plato, Democritus attempted to explain the world without reason as to purpose prime. It just is. It's kind of like explaining quantum mechanics. It's hard to have reason for that. They wouldn't like quantum mechanics. In any case, Democritus is said to have been disliked so much by Plato that Plato wished all his books were burned. All right, so in any case, if you cannot perceive atoms, they probably don't exist. And that was really, I would say, one of the reasons why particle theory and mole theory took so long to get to chemistry, to open the doors for it to be a science, to do predictions. I'll get more to that. So we have many different scientists, and I'm not covering them all, but real quickly, Robert Boyle, we know him for his Boyle's Law, but more importantly, he was a very important figure in denouncing the idea that atoms don't exist, these particles don't exist. He did a lot of work with gases, as we know, and if you have a gas, and we know that his famous law, of course, Boyle's Law, take a gas in a confined space at constant temperature and pressure, you can have that volume with the same number of molecules. Boy, the pressure that these molecules have inside is going to what? Double, because you made the space half as small. So pressure was inversely related to volume, all right? And again, that's Boyle's Law, but his law of pressure doubling when the volume is halved only works if you've got these little tiny particles moving randomly. So we know air is made of something, okay? But to come out and say it, he may have been considered to be going against the centrist idea of, hey, people thought perception that stemmed from Aristotle to Socrates. So what he did is he wrote a play. And in that play, okay, he had characters who refuted the idea that atoms don't exist. So he showed support for atoms by the characters in his play, not by himself, in hopes not to get in trouble. Okay, so that's important. Remember, Galileo was jailed because his idea that planets, including Earth, revolved around the sun, not the other way around. The world didn't revolve around the Earth, so that kind of thinking stemmed from the ideas of Socrates throughout. Okay, so Robert Boyle did a bunch of things. Joseph Priestley, okay, he's been credited with discovering oxygen. Now, he also believed in the phlogiston theory, a phlogiston theory. And it's a crazy theory, but it was one where he used, or at least accepted, he didn't make this up, to try to hold on to the idea that there is no atoms. So we isolated oxygen gas, didn't know what it looked like, but it was a gas, which means it's a colorless, odorless gas made of something, okay? Which is weird. It had to be made of particles, right? And so the idea was very simple, that if I had something that burned, we know something burns when you have oxygen around. We all know about combustion, right? So the idea was when you have oxygen, things combusted. So maybe it's the actual particle in the gas that's causing combustion, but no. What they did was accepted and held on to the idea that there is something called phlogiston in chemicals. Really crazy. Okay, so the idea was you have burning wood, and it burns because there's something called phlogiston inside of it. And it gets released, okay, and eventually the wood runs out of phlogiston, okay? And the air doesn't support combustion anymore once phlogiston goes into the air. Kind of crazy. So oxygen supports combustion because it's dephlogisticated. There's no phlogiston has gone to the air yet, so that's why it burns, and that's the way to explain oxygen. Well, guess what I think about that? All right, well, that is so instead of supporting an atom or particle concept that's reacting, they gave this a ridiculous size. So I think this is crazy. All right? And so why am I bringing up Joseph Priestley? And that oxygen was really just dephlogisticated air, because this idea was so unconvincing. I believe it helped give momentum to the particle theory. If we hold on to Aristotle's perception that matter was infinitely indivisible with no small pieces, then you had to accept this ridiculous theory. So, gosh, you start questioning that. So that's why I bring him up, but I don't give him any picture to post here. All right, so Antoine Lavoisier, all right, this was a French nobleman who lost his head in the guillotine because, among many things, he was an aristocrat, he was a tax collector, so it didn't end well for him, but he is the father of modern science because he actually did chemical reactions. And in these chemical reactions, he pretty much put an end to this theory by showing that things don't have phlogiston in them, and that if you were to do some reactions, okay, the mass of the reactions equal the mass of the product. So one of the things that he did, and he did many things, is he did in a sealed container one of these reactions. Of course, we didn't have this chemical formulas yet, we're getting there, but what we have is mercury oxide, and with some heat, it basically decomposes into pure mercury. We know what that looks like. It's a silvery liquid metal at room temperature, and this oxygen gas, so this isn't made of phlogiston, it's made of what? It's made of oxygen. So it kind of put the end of that, but more importantly, through this experimentation, he showed very simply that the mass of the reactants equal the mass of the products. And how does that happen? How does the mass of the products, reactants, equal the mass? Well, it must be that something's interchanging to make something new. We know we're making something new. The properties change. The color changes. You create bubbles. Yet the masses are the same before and after. Hey, that must be that particles are interchanging. There it is, our particle theory. Let me see, Mr. Grotsky, where is the mole theory here? You don't have a mole theory to count particles unless you agree that particles exist. So we've got to create that scenario. All right? So in any case, moving forward, we got Joseph Proust. Very, very important. Basically what he did was, and again, there's many other people, Henry Cavendish, there's a whole bunch of other people that contributed to the fact that there are these small particles. Now, what I thought is really important is he did basically studied copper carbonate, whether he took that from a natural source and purified it, or he made it in the lab. And what he found was the ratios of percentage of masses of copper, carbon, and oxygen were the same no matter what source of copper carbonate I had. Okay? And that's important to show that compounds are made up of a definite percentage of these different elements that he could purify. And if these elements are made up of different atoms, then it means that they're made up of what? Some distinct number of ratio of atoms, some number of carbons, some number of coppers. Every compound has a unique number of atoms. Now, of course, that's a big stretch, but here's a great example. Take 10 grams of lead, 1.56 grams sulfur, and this makes a new compound with no waste. And if I take a little more sulfur than I can need, I'm going to have extra sulfur unreacted. Or if I take extra lead than exactly what I need, I'll have extra lead produced. Why is that important? Somehow there's an exact amount of particles in here that make exactly that product. If I have more than I need, I'll have excess. Every compound is made up of a unique percentage of these reactants, or a unique number of atoms. Okay, very important. So, law of definite proportions. Compounds have a definite ratio. So, copper hydroxide in this case, and not carbonate, has this percentages. I'm not sure. Should I probably use something else? Moving forward. John Dalton. So what did John Dalton do? Well, John Dalton, okay, early 1800s, put together, okay, the first modern atomic theory. Of course, the idea of atoms is not his. It was Democritus or his teachers, so they think. But what he did is he took the work of all these other individuals, Antoine Lavoisier, Joseph Proust, Cavendish, okay, and he did some of his own work. He was an English teacher that was interested in weather, so he was basically trying to figure out how gases work. But through all of his investigation, he came and took everyone's work and he said, gosh, it is really, really convincing that atoms exist. All atoms are made of tiny particles called atoms, atomos. Revisited that word. All atoms of a given element are identical in masses. Now, of course, we know that they do differ, but in isotopes, but we don't know that yet. But we did know that different atoms have different masses. Okay? Atoms of a given element are different from those of any other element. Okay? They're different. You know, copper is different than carbon. We saw those differences. They make different properties when we purify them. Atoms of one element combine with atoms of other elements. This was Antoine Lavoisier. The mass of the reactants, mass of the products, they're just interchanging the pieces, okay, to form compounds. A compound always has the same relative number of atoms. Hey, that's Joseph Proust. That's law of definite proportions. And then atoms can't be created or divided into small particles nor destroyed, although we know in particle accelerators that's not the case. So these 5 points, okay, we're going to really put an end and start chemistry. This was going to be the start of it all for us to have chemistry. Remember, chemistry wasn't really a discipline that you studied. You played with things, saw some reactions, but we didn't understand why they worked, why they didn't, and if they did work, we couldn't predict much with them. So, problem with John Dalton was that he, as smart as he was, okay, he had this, supposedly, as it's written, an easy demeanor to attack. Okay, supposedly, from what I read, he's got a demeanor that, hey, I'm the smartest guy in the room, and you're not. So people didn't like him. Now, a couple of things. Before we get to that, I would say the work that he did that's probably, to me, more important than anyone else's work is he came up with the law of multiple proportions. Yes, he's given law of combining volumes, or law of partial pressures, I should say, I'm sorry. But this right here, to me, is the crowning achievement of his work right here. To me, that puts kind of a nail in the coffin that atoms or particles existed. So what he did was, when he reacted 2 different purified forms of elements, different atoms, and if those 2 reactants made 2 different compounds, okay, the mass ratios of one of those atoms was always a whole number difference. So if we had, again, you're looking at this with carbon and oxygen and CO, carbon monoxide. They didn't know the chemical formulas. They just carbon, put oxygen, and they got 2 forms, 2 different gases, 2 different densities, 2 different reactivities. And then he did what? He basically purified them. How he did this in 1800s, beyond me, these guys were brilliant. But if you take carbon monoxide and carbon dioxide, now of course the names kind of give away how many oxygens, so they didn't have the names for them, but take those 2 gases and you do the ratio of the mass of the carbon to the mass of the oxygen, there's a 3 to 4 ratio of the mass of the carbon to the oxygen of this unknown gas. That came from the same components that this unknown gas that was different, but this was at a ratio of 3, mass to mass ratio of carbon to oxygen is 3 to 8. Why is the mass of carbon to oxygen 3 to 4 compared to the other gas 3 to 8? Why was the oxygen a whole number difference? This compound, unknowing to anybody else, had twice the mass of this carbon, and those numbers were always whole number differences. Whole number differences, people. If you've got whole number differences, you've got whole number particles. This had twice the what? Number of oxygen atoms in its particle. And that's where you come up with whole number differences in our math. We get ratio of whole numbers in lab. Anytime in lab, you're getting 1.99. Okay, 0.99, you're getting 1. It leads you to the idea that there are these singular particles. You can't have 0.5 of an atom. You can't have 0.73 of an atom. But when you start getting whole number ratios of differences in matter, boy, it speaks to there are whole number differences of particles. Can't say enough how that is really important. And there's a whole other ways to look at that. But again, what was his problem? Well, John Dalton, not only did he try to give us an atomic theory, he also tried to give us symbols. And some of them are kind of silly. It's hydrogen with a dot, oxygen with a 0, and some of these he tried. That's not a big deal. The biggest problem he made was that he started writing chemical structures that were not correct. People tried to use these in lab to do the scientific calculations that would have started chemistry, to be able to predict and calculate with these laws. But none of these worked. This is water. This is, again, hydrogen with a dot, oxygen. He thought water was a HO. 1 H and 1 O. HO. He said that anything that had 2 different elements must be binary, just 2 of them. And it was incorrect, and he had no data to support that. So people that were holding on to the idea that atoms don't exist saw this stuff that didn't work out, and it was easy to say, well, if this is incorrect, everything you have is incorrect. And besides, it was easy to attack John Dalton because he was supposedly this crass individual that didn't like to be wrong. And he overextended himself in this area. He was onto something, okay? But again, this was an opportunity for people to say, this is wrong. All right, well, in this same time period, we have Joseph Gay-Lussac, who did hundreds of reactions with gases. And he figured out, just like we saw on the other slide, where we had lead and sulfur making lead sulfide, he found exactly how much of each gas was needed to react to exactly make some volume. So these are volumes of gases. And he found to make water vapor, I need 2 liters of hydrogen gas, whatever that was, it looked like, plus 1 liter of oxygen to give me 2 liters of water vapor. And so he did this for many, many reactions. And people went to their labs and they did the same work, and it was found that his ratios were right. As long as you had pure hydrogen, pure oxygen, this was exactly the ratios of gases you need with no waste. What do we do with that? Because what's inside doing that? Obviously, people said there's no atoms, but gases have pressure. So, again, what did Dalton say about that? Well, Dalton said, basically, that your data is incorrect. Remember, Dalton couldn't correctly make molecular molecules, and that they didn't support that. But he said, listen, H and water go together. So he basically says, hey, because H and O go together, you've got an extra volume here. One of these and one of these makes 2 of these. And this doesn't make any sense. Your data, Gay-Lussac, is wrong. He's right, he was wrong. But everyone knew that when they did these reactions, it came out. And unfortunately, we're talking about the early 1800s, that stopped chemistry. We couldn't figure out what these ratios were. We couldn't figure out the chemical formulas. We couldn't figure out what the atoms, if there were atoms, if in fact they had some arrangements. We couldn't do anything. This stayed stagnant until about 1860, where chemistry was not a science you went and studied. It was something that was fluff to all people. If you want to study science, math and physics. So what did we do? Well, there was a conference. And then that conference, very famous conference, all the known chemists and people, again, if you did chemistry, you knew it because of empirical trial and error, came together to talk about all the problems in chemistry. The biggest one is, how can we come up with a way of figuring out what these particles are in terms of a chemical formula? All right? And so, very importantly, a guy named Cannizzaro came and was talking supposedly in this conference. And what he did was he brought with him the work of Amedeo Avogadro. Now, Cannizzaro being an Italian, he brought an obscure Italian physicist. Notice he's a physicist, not a chemist, all right? A physicist's work that was published. Now, back, of course, publishing in the 1800s means you were published in a book, and there probably was very few of those books around, so it wasn't well known. But what Amedeo Avogadro found, okay, was this. He found that the volume of a gas, the space a gas takes up, is proportionate to how many molecules. He coined the word molecules in his work. Okay? And that's where we get the word mole from. Now, he coined a molecule to be either a single atom or particle made from, let's say, helium doesn't bond anything, so it could be a single atom, or it could be an atom bonded with other atoms. It didn't matter whether it was a particle like this or a bigger particle of 2 or more. These guys all moved as a single particle. And so his basic statement was, if you add more of these particles, the volume goes up proportionate. And it didn't matter what these particles were as long as they were a single particle. What that meant was, if I had a particle of 2 atoms, or 2 particles of 2 atoms, or 2 particles of a bigger molecule that had 2 atoms per individual particle. Again, his molecule was either this or one of these, but it didn't matter whether your particles were individual atoms or were they bigger ones bonded together. These would occupy the same space. This was 1 liter, tell me drawn, this is 1 liter, as long as the pressure and temperature on them And that was his basic assumption, that equal volumes, hey, if the volumes are equal, then the number of particles inside, no matter how big the particles are. And I know some people have a problem with that. How in the world can you have bigger particles take the same space? Because we tend to think in solids. If we take a model here of an ionic crystal, we see how it's kind of packing in a simple cubic structure there. Well, if the radii of these ions are bigger, then it's going to push out the crystal. But remember, gases, okay, themselves are infinitely small. And if I take a box and I have, let's say, two molecules, whatever they are, those two particles, and I take a picture where they are, and then keeping the same temperature and pressure, take another picture of seconds later, they might be there. And this distance between them is called the mean free path. And it's going to stay constant if the temperature, how fast they go, and the pressure on them stays constant. So when you consider this distance compared to the space these molecules take up, that's huge. Greatest analogy I can give you, if you take a football field and 100 yard, so here's a goal line, and here's a goal line, this is 100 yards, and I put an ant on one goal line. And you consider the space the ant takes to the space to the goal line, you can see that the ant's own space is insignificant really to that distance. And if I make this ant be 10 times bigger, is he really significantly closer to the other goal line? No, because the distance is so big. So this distance, though it seems small to us, relative to us, is infinitely big to the space these guys take up. Their space is so small, people consider a real gas, okay, or an ideal gas, to have no actual volume. They take nothing. And that's not really true, but they're so small we can almost assume they actually don't take any space at all. So consider this distance with something that barely takes up any space, okay, making that particle bigger, although on paper it looks like, oh, I just made it that much closer. It's not significantly closer, all right? And you can talk more about that in gas laws. Now this one will move a little slower, but hits the what? Hits this with a little more impact, more inertia, because it's a little more massive. So that was his basic tenet, that volume was proportional to the particles, and it didn't matter what the particles were. Didn't matter. It was the same for all the same number. So Cannizzaro brought that idea, okay, to the forefront. And supposedly, he was taking Gay-Lussac's work for one of these gases, and I'll use water. So he took what was known as the law of combining volumes, which is hard to understand. Why are the volumes combining? So we take two equal volumes. Now I'm doing my best to draw these as equal, but hey, I'm not the best. And this is going to be this one volume of oxygen, and they're going to react, and they're going to make two equal volumes of water. Again, I'm trying to show all of these to be the same. I know that I'm lacking in that area. But, okay, let's make this hydrogen. Make this a particle. We don't know what it was. We called hydrogen because it was water maker. It made water. Hydro, water. Gen is, I think, Greek for maker or creator. And then we have, okay, one here. Notice I'm drawing one particle per box. Now, of course, there's going to be more than these, but in its most simplest case, hey, one of these creates this distance. Now, of course, it takes more than that. Remember, molecules will bang around in a box and push off each other to create that mean free path. But right now, I'm saying this one atom creates the space for itself against other atoms. And because this is one molecule, it takes this space. This one is one molecule, it takes the same space, same idea. Now, why would 3 volumes make 2? This is what they found. Why would 3 volumes make 2? Well, because, hey, the molecules are coming together. We have 3 separate particles making 2. So if you believe in John Dalton, that water is a HO, H and O, we put them together because of Antoine Lavoisier, law of conservation of mass. One of these come together, and then you're going to have one extra. And that would explain, hey, 3 equal particles require 3 separate volumes. We went down to 2 molecules, right? Doesn't matter if it's a single particle or a bigger particle, right? I need less volume because there's less molecules. Volume is proportionate to how many particles you have. Well, guess what? We have less free particles, less volumes. That makes sense. That's why it's combining. But as you can see, empirically, they found that this to be completely water. It wasn't one water and then hydrogen. This was two water molecules, so this didn't work. And as Carnazara was showing on a blackboard, well, we can deduce for this to be absolutely true, to verify this, and it is verifiable, and we know this to be almost law, that's 2-to-1 ratios to make two volumes of water. We had to deduce that hydrogen was diatomic. There was 2 per particle. And if you notice, that would give us 4 overall. We put what? 1 here, 1 here. And you notice we still don't have the what? The oxygen. We'd have to deduce that oxygen was diatomic, and there it is. And there is how we explained. And supposedly when he was talking, all right, in his conference, people were leaving the conference to go to their labs. Before you can finish this, people saw how this was working. And if you don't see it yet, 2 H2s plus what? Plus 1 oxygen molecule, that's O2, gives us 2 water molecules. Okay? Hello, we've got chemical formula. We've got what the atoms look like. And you notice, law of conservation of atoms. We have 4 hydrogens, 2 oxygens, 2 oxygens. The mass of the what? Reactants equals the mass of the products. Antoine Lavoisier's work. And we also have Joseph Prost's work. Look at this. Water has a definite ratio of 2 hydrogens to oxygens. But this, my friends, was the first time we had chemical formulas. This is the first time we had chemical what? Equations. And it's interesting. We found out what the atoms look like, right? By using colorless gases. Gases were the Rosetta Stone of opening the doors for chemistry so that we could do it. Now, you say, okay, how do we do chemistry yet? How is this mathematics? Well, we've decided and discovered that these particles can exist, and they make sense with our empirical evidence of Gay-Lussac's and more. And we're writing this. You say, well, how do I definitely know that there was 2 H's and 2 O's? Well, we did other reactions. You saw the same thing. So if you look at, continue here. If we think oxygen's diatomic and carbon isn't, this would be a 1-to-1 ratio if it was. And we know from oxygen to carbon, okay, we know that it's 1 box. So this is empirical. And the way to explain this is what? Not that either, whatever. Okay, it was this. How do we explain that? Well, it works very nicely. So in other reactions, it was upheld that O2 was diatomic to explain what they knew. All right? So this opened the door. People now knew what the chemical formulas were that Dalton so desperately wanted to do. And these ratios of liters were a ratio of particles. And so we had coefficients. We had law of conservation of mass. But what we didn't have, party people, was the idea that how do we count? Here's another example. Okay, we knew this empirically. But we knew from other work that we did that this was diatomic. This probably is diatomic. I mean, we didn't have chemical formulas, but it made sense now. Empirically, we go through this, and we know what they look like. And for this volumes to be true, and it was found to be true, we discovered what the atoms and the arrangements of the molecules look like. Thank you, Amedeo Avogadro. And that's what he found. Now, we discovered atoms today. We can feel for them. But more importantly, we're left off now. How do I use this? How do I use this to do chemistry? We're close. Because now that I have a chemical equation, now that I kind of can see these atoms from this work, how do I use it? Now, I know this is kind of silly, but this is how we would use it. I know I need 2 hydrogens for every 1 oxygen molecule to make 2 H2O molecules. Party people, how in the world can we take 2 hydrogen molecules? We can't. It's too small. Too small. So we needed a way to use these ratios. This is not a mass ratio. It's the ratio of how many actually, 2 of these to 1 of these. We needed a mole concept to work with our atomic concept, to have some kind of way of doing this. If I want to make pure water with no waste, just like we did with the lead and the sulfur, okay? My friends, I need to be able to count 2 of these and 1 of these. But I can't count atoms. There had to be a way. So we needed a universal container, a way to have a group of atoms be some known amount that we agreed upon to be 1. We can't use just 1 of these, but what if we used a lot of them? So it's pretty ingenious how they did that. So a way to think about that is if we have turkeys and pigs, and if I have 2 big containers, huge containers, assuming that the animals all have the same number in each, meaning there's the same number of turkeys here, same number of pigs here, just like we have in what? Equal volumes, same number of particles, equal volumes of truck containers, same number of particles. The particle might be bigger, okay, and I know we're using pigs and turkeys to be our atoms here, but let's pretend that the entire container was 2 kilograms for the turkeys, I'm just making something up, and 32 kilograms for the pigs. What's the ratio? Well, the ratio is a 1 to 16 ratio. What does that mean? If I take a whole container of turkeys and a whole container of pigs, as long as the numbers are the same for each, the same number of pigs equals the same number of turkeys, and assuming all the pigs were the same, all the atoms were the same, right? You know that they differ by proton number, and essentially their masses are very similar. The ratio of all the turkeys and the ratio compared to the ratio of the pigs should work out to the individual turkey, the individual pig. Assuming all the turkeys are the same and all the pigs are the same, and you have equal number of animals, the total ratio of all the turkeys and all the pigs, if you reduce the lowest terms, would give you the ratio per what? Individual animal. So for everyone, that would say that the what? The pig is 16 times more massive than the individual turkey. Well, this is what we did. We took equal volumes, okay? We took equal volumes of 2 different gases. Now, of course, in my drawing here, I only have 1, but what if this box is 1,000 liters? We're going to have a lot of what? Particles. And it's pure hydrogen, pure oxygen. And we mass them out. We're going to get some huge number, but when you divide by what? The smaller number, take this, we're going to get 16 every time, as long as temperature and pressure are the same, Avogadro's hypothesis, okay, and because temperature and pressure are the same, we're going to have the same number of molecules. So if I had 1,000 liters of each, and I mass out take away the containers, the ratio is going to work out to 1 to 16. No matter what the size of the container is. And what that tells me that is that each individual oxygen is 16 times more massive than hydrogen. That's called a relative atomic mass. And that's what we have in the periodic table. You'll see hydrogen, its relative atomic mass is 1, at 1.00 some number because of the isotopes. And then oxygen is about 15.999. But that difference is a relative one. We can't measure them on a scale. We compare them with each other. Since hydrogen is the lightest, it gets the 1. And of course, oxygen is 16 times more massive, or something close to that. And that's why we were able to say, based on Dalton, that every atom was different early based upon atomic mass. Okay, great, Grotsky. We had a way of now showing how different atoms were different sizes. How do we work this out now? Okay, this is the beautiful part for me. Okay, it doesn't matter. It doesn't matter, okay, what we decide to be the ratio of how many. We needed to pick some number of these to equal 2. We couldn't be just 2 hydrogens. We needed some bigger number. Like if you're an egg farmer, you use dozen to represent 12. So if you had 24 eggs, you wouldn't say 24 eggs, you would say 2 dozen eggs. Well, here we want to say 2 moles of H2, which quantifies to be some number. And to 1 mole of O2 makes 2 moles of H2O. Moles, short word for molecules, right? So we couldn't do them individually, but what if we use some number? What if a mole was 10 of these? So I would need 20 of these to what? 10 of these to make 20 oxygens. If a mole was 10, right? Now we don't use 10. So what do we do? So it's pretty ingenious because we had this atomic mass for oxygen to be 16 and hydrogen to be 1, and we did this for as many atoms as we could this way. Okay. What we decided was, we know the ratio is always 1 to 16. Let's go find the volume. Let's go find the volume where the ratio actually comes out to be 1 gram to 16 without doing the what? The work to simplify. Let's go find exactly what that volume would be. And they found that volume to be 22.4 liters. So at STP, 22.4 liters, this is about that. 22.4 liters is the space that a mole of gas molecules would take up at STP. So this 22.4 liters, the gas that fits in this box in 22.4 liters, we're going to call that, I don't even care what that number of particles are, whatever fits in there, we're going to call that a mole. So if I want to make water, I need one of these. This is my universal container. We didn't care what the actual number was, but we know that if I had 22.4 liters of hydrogen, it would be 1 gram. If I had 22.4 liters of oxygen atoms, it'd be 16. What did we just do here? We picked this volume to give us the ratio directly in grams without simplification. We know it's always 16 to 1, so we picked the volume. It seems arbitrarily to be 22.4, right? You learn 22.4 equals 1 mole, but it's not arbitrary. It was exactly the space that we needed to make hydrogen be 1 gram if it was 1 atom. Now we know that having a box of H2 is not 1 gram. It's going to be what? 2 grams, because don't you have 2 moles of atoms, right? If you're saying there's twice the number in here because every little particle has 2. So what we did is we made the atomic mass, which is a relative atomic mass based upon the differences in the sizes of the atom, right? We made that number equal to the grams of 1 mole. Okay, we could care less what that was. Okay, but we made that. And so look at the work we can do now. Watch. So now, given this balanced chemical reaction, we have to be balanced to show law of conservation of mass. It must be balanced. Watch what I do here. So if I have 2 moles of H2, what do I know? Well, H2 is made up of 2 hydrogen atoms, right? Each one has a mass of 1 gram per mole. So that would give me 2 grams. Let's pretend a mole is 1 particle. It's not. It's a huge number, right? Well, if you have 1 of them, it'd be 1 gram. But you really have 2 of them. So you have twice the number of particles. Okay? So that's 2 grams for every mole. Okay, well, I have 2 of them. If it's 2 grams per mole, isn't this 4 grams altogether? What about oxygen? Okay? Well, we need 1 mole of oxygen. So what's 1 mole of oxygen? Well, oxygen is O2. Now, every oxygen is 16 grams. If I've got a box of oxygen, okay, I've got a box, 22.4 liters at STP. If it was just oxygen atoms, it'd be 16. 16 grams perfectly fits in this box as a gas at standard temperature and pressure. But I don't just have oxygen, I've got 2 of them. So because I have twice the number in that space, and it doesn't matter, get big, right, they're infinitely small, it's 2 times 16, which is 32 grams per mole, per each mole. Since it's 1 mole, this is 32. All right, so what we're going to make? Well, 2 moles of water. Okay, well, water is H2O. And 1 mole of water, don't you have 2 moles of hydrogen? So we go 2 times, there's 2 H's, so 2 times 1, that's the atomic mass, is 2 grams. And don't I have 1 oxygen? And what's the atomic mass of oxygen? 16. And what's the value? 18 grams per mole. But there's 2 of them. 2 times 18 is what? 36. And look what we have here. 4 grams of hydrogen gives me, plus 32 grams of oxygen, will give me exactly 36 grams. And notice 32 plus 4 is 36. Antoine Lavoisier, thank you. And we have a way of doing that. Now you say, I still don't see it. Well, wait a minute. If I want to make 2 moles of gas, I know I'm going to make 36 grams. If I need 2 moles of hydrogen, I know from this mole theory that I need 4 grams. I can use a scale to count the ratios I need. Now why, if there's twice as much H's, is it so gosh darn lighter? 2 moles to 1 mole. This is twice the number of particles, yet it's 4 grams because hydrogen, okay, has such a small mass, okay? So we're able to count molecules and use them by using the scale, by getting the mass and knowing the atomic masses. Because we made the atomic masses equal to 1 mole, we're able to do chemistry now. Chemistry at 1860 now took off with a mole concept. Now we had a way of getting twice as much hydrogen to oxygen. Could care less what the actual number was, but we knew it was the same. So twice the H's to 1 makes 2 waters perfectly. And we could calculate, listen, what if I had 4 grams of oxygen, and I wanted to make, how much water would I make if I had what? An unsupplied limited oxygen. 4 grams of hydrogen, we could calculate to make 36 grams perfectly if we had enough oxygen. We can calculate exactly how much we need. We also, if I wanted to make 36 grams of water, I can do the math to figure out exactly how many grams of each of these I need. But to go to grams, it all starts with these mole ratios. This is a how many number. I left the box out. So we had what? 2 to 1 to 2. The way we count to use particles and the way to do math and chemistry to predict how much we're going to make or how much we need to make something, we can use a scale using our atomic masses. We can count with our scales. And using the particle theory, atomic theory, together with a universal number theory, we can calculate how many grams of product and actually start doing a science. And later, 50 years later, we figured out exactly how many particles, molecules, actually existed in this space. And it was, of course, 6.02 times 10 to the 23, a huge number, because these are so infinitely small. So a mole equals 22.4 liters. Why? Because we made it that way so we can use the atomic masses in our calculations to help us figure out how many that we need based on these chemical formulas, based on balancing. All right? And it took a while, but chemistry finally became a science because of both parallel concepts developed at once. Hope that helped.